Hi, in this lesson we will study the continuity of a function. Roughly speaking, a function is called continuous if its graph can be drawn with a continuous line. For example, this function will be continuous. Accordingly, the function will be discontinuous if its graph cannot be drawn with one line. For example, such a function will be discontinuous. At this point, let's say x0, it has a discontinuity. But let's introduce a strict definition of continuity. A function y equal to f from x is called continuous at the point x0 if the following condition is satisfied. First, the function is defined at that point, and second, there are ultimate left and right limits at those points. That is, there is a limit. X approaches x0 from the left. How can we understand the limit from the left? We have a function. We can tend forward to x0 on both sides, from the left or from the right. So the limit from the left means that we will tend forward from this side, and it is designed as x0 minus 0. Sometimes it is just x0 minus. We will write it down as x0 minus 0, meaning the point x0 minus some very small number, x0 minus some number. That is, we will come just the same to the left. So there is a left limit of this function. There is also a right limit of this function. The same thing, that is, x approaches x0 plus 0. It turns out that we are striving to the point x0 on the right side. F from x. And the function is defined at this point. That is, we can substitute the point x0 into the function and calculate if all these things exist and are ultimate. Moreover, they are equal to each other. Then we can say that the function f from x is continuous at the point x0. For example, let's take the point x0 here. The corresponding value will be f from x0. And take a look at the limit from the left. If we approach this point from the left, we will just get this value. If from the right, then again this value. And the value in this function is f from x0. That is, this function is continuous at the point f from x0. Let's consider this function. If we approach x0 from the left, then we get this point. It has its own value. If we approach x0 from the right, then we will get this point. That's already a different value. That is, we have left and right limits, but they are not equal to each other. Then it turns out that x0 is the point of discontinuity. Points of discontinuity are divided into two types, points of discontinuity of the first kind and second kind. Let's take a look at them in order. Discontinuity points of the first kind are two types. The first so-called removable points of discontinuity. Removable discontinuity points occur when we have left and right limits. And they are equal to each other. But the function f is not defined in x0. I schematically depicted that there are left and right limits. Moreover, they are equal to each other, and the function f is not defined. This situation is graphically described as follows. We have, let's say, some function, and at some point, x0, it is not defined. The limit from the left will be equal to this value. The limit from the right is exactly equal to this value. They both exist, but the function itself is not defined at this point. This is the removable point of discontinuity, discontinuity point of the first kind. Why removable? Because we can always complete this function at the point x0. Say that function is equal to such and such value at the point x0, and then we get a continuous function. The discontinuity points of the first kind also include discontinuity points of the jump type. Such discontinuities occur when we have left and right limits, but they are not equal to each other. We have already considered such a case graphically. For example, such a function which consists of such lines. The point x0 in this case is a discontinuity point of the first kind, jump discontinuity. Indeed, we have a left limit. The left limit will give us this value. The right limit will give us this value. They both exist, both are ultimate, but they are not equal to each other. Thus, such a jump was formed in this function. These are discontinuity points of the first kind. Discontinuity points of the second kind include such a discontinuity points at which one of the limits doesn't exist. This is a sign of existence, or equals infinity. That is, where we have a limit, left to right, it will not exist, or some kind of infinity will turn out. Then we can immediately say that this is a discontinuity point of the second kind. So with the help of limits, we can examine the function for continuity and determine what kind of discontinuity points it belongs to. Let's take a look at a few typical examples. Let's have a function f from x. It is given in piecewise form. That is, for each section, it is determined by its own formula. Namely, if we have an argument x less than -1, then f from x is defined as x plus 4, for x from -1 inclusive to 1 excluding. F from x is defined as x squared plus 2. And for x greater than or equal to 1, f from x is defined as 2x's. Such a task is called a piecewise function. To draw a graph of such a function, we must draw a graph of each corresponding function on a given area. Let's examine this function for continuity. Obviously, the functions x plus 4, x squared plus 2, the function to x are themselves continuous. Remember their graphs. They are continuous lines. Accordingly, in the function f from x, discontinuities can occur at points at which the given sections seem to join, namely at the point -1 and at point 1. This function should be examined for discontinuities at given points. Let's start with the point -1. In order to investigate the function for discontinuity at this point, we must first calculate the left limit. That is, the limit x approaching x0 from the left. x0 is -1. -1 on the left means -1 minus 0. Here is the function f from x. Let's calculate this limit. Limit x approaching -1 from the left. If x approaches -1 from the left, then this point is slightly less than -1. If we have x less than -1, then the function is defined as x plus 4. So in this case of f from x, we put x plus 4. It remains to calculate this limit. It is very simple, -1 minus 0 instead of x. Plus 4. -1 plus 4 is 3. 3 minus 0 is 3. 0 in this case is like a very small number approaching 0, so the limit from the left of this function is 3. Now we need to calculate the limit from the right. That is -1 plus 0 from f from x. If we have -1 plus 0, then this point is slightly right than -1. That is, x is greater than -1. If x is greater than -1, then the function is defined with this ratio, x squared plus 2. It's also very easy. -1 plus 0 squared is like -1 squared. That's 1 plus 2, that's 3. So we have calculated the left limit. The right limit, it remains to calculate the value of the function at this point. That is, f from -1. Looking here, which of the intervals includes -1? This interval. So -1 is substituted into this function. Putting -1 into x squared plus 2, -1 squared plus 2, that's 3. So we have a left limit, a right limit, and the value of the function at the point -1. All values turned out to be equal to each other. If they are all equal, then the definition would be that the function f from x at -1 is continuous. That is, x equals -1 is a point of continuity. So at the point -1, we have a continuous function. Examine the function at point 1. The same thing. Now we have x0 equal to 1. Again, counting. The limit from the left, 1 minus 0. So it's a little less than 1. So we fall into this interval. It turns out x squared plus 2. Counting this limit, it will be equal to 3. Now, Let's count the limit from the right, x approaching 1 but plus 0. If we have 1 plus 0, then this is a little more than 1, so we fall into this interval. So we will have a function of 2x. The limit is also considered very simply. Just put 1 plus 0 instead of x, multiply by 2, that's 2. We have calculated the left limit, the right limit. It remains to calculate the value of the function itself at this point, f at point 1. F at point 1 is determined using this function, because x is equal to 1 entering this interval. 2x is just 2. Thus, it turned out that the left and right limits exist. Their final function is defined at this point, but the left and right limits don't match. Thus, if the left and right limits exist, are ultimate and don't match, then x0 equal to 1 is our discontinuity point of the first kind. Now let me remind you, in the first kind we had a point of removable discontinuity, or a point of the jump type. We have a jump in this case, because we will have a function 3 on the left, 2 on the right. So we have a jump from 3 to 2. That is, x0 is a discontinuity point of the first kind. Let's consider another example. We need to investigate for continuity the function f from x equal to 2 to the point of 1 divided by x minus 3. It is obvious that we should investigate the point x0 equal to 3. In our case, it is bad. Just note that the function f from x at point 3 is not defined. We cannot substitute 3 into the function and calculate. There will be division by 0. The function is undefined and the function will definitely have a break at that point. Now let's explore what kind of gap will we get. To do this, we need to consider the left and right limits. X approaching 3 from the left, that is 3 minus 0. 2 divided by 1. X minus 3. Let's calculate. If instead of x we put 3 minus 0, we will have here 3 minus 0 minus 3. 3 will go away. There will be 1 divided by minus 0. Let's write it down conditionally. 2 to the power of 1 divided by minus 0. 1 divided by a very small negative number. If we divide by a very small number, then we get a very large number. If negative, then it will be with the minus. That is 1 divided by minus 0. This is a minus. Infinity. 2 to the power minus infinity, we can conditionally write it down as follows. 2 to the power minus 1 is 1/2. Like 1/2 to the power of infinity. 1/2 to the power of infinity is 0, because if we constantly multiply 1/2 by itself, the number will keep decreasing, and it will be 0. This is our reasoning. We usually don't write them down. Accordingly, this limit will be, let's write it down here, will be equal to 0. That is, the limit from the left is 0. Let's consider the limit from the right. Similarly, we substitute 3 plus 0. There will be 3 minus 3. It will go away. 1 divided by 0, that is 2 to the power of 1 divided by 0. 1 divided by 0 is plus infinity. That is, 2 to the power of plus infinity is obviously plus infinity. Accordingly, this limit is plus infinity. Thus, we have a limit from the left, an ultimate 0. The limit from the right also exists, but it is infinite. In the case when we have infinity, the corresponding point is a discontinuity point of the second kind. That is, this function is discontinuous at the point x0 is 3, and x0 is 3 is a discontinuity point of the second kind. And let's consider the last example. We will examine the function for continuity again. It is obvious that we should investigate the point x0 equals 2, because at this point we have a 0 denominator. The function f from x at the point 2 is not defined. That is, we will have a gap here. Let's examine which one. We consider the left and right limits. That is, x approaches to 2 from the left. Let's see what happens. It will be 2 minus 0 plus 7 on the top. It is 9. And there will be 2 minus 0 minus 2 on the bottom. Minus 0. And there will be 9 divided by minus 0. 9 divided by a very small negative number. It's a very large negative number, that is minus infinity. Now we consider the limit from the right, although it is already obvious that x equal to 2 will be a discontinuity point of the second kind. If we count the limit from the right, we get plus infinity. Thus, the function at point 2 is not defined. The left and right limits go to plus and minus infinity. That is, x0 is a discontinuity point of the second kind. Thus, when we examine a function for continuity, at a point, let's say x0, the first thing we pay attention to is the value of the function at that point. Can we calculate the value? If we can, then we do it. Further, we pay attention to the left and right limits. See results of calculations. What will we get? If we have a function defined, the left and right limits exist and are equal to the value in this function, then the function is continuous. If our left and right limits exist and are equal to each other, and the function f from x is not defined, then this is a discontinuity of the first kind, namely a removable discontinuity. If it turns out that the left and right limits are ultimate but are not equal to each other, then this is a discontinuity of the first kind, such as jump. If one of these limits doesn't exist or goes to infinity, then this is a discontinuity point of the second kind. This lesson is over.